So programming OpenACC is great because it gives you a whole bunch of things. You have existing code, you port it over, throw through directives at it, and see if it's feasible to to offload to this new architecture that you have. Unfortunate thing is that if you're currently doing OpenACC programming and you're getting to a point where you want to know how well does my program actually do, it kind of feels like this. You see a little bit. It's you're kind of reading tea leaves, and it doesn't really tell you specifically what's going on. Kind of to get this to a more broader sense, why are you using OpenACC? You're either prototyping something, you have this idea, and you don't want to go through all the hassles of using CUDA. You just want to write it down real quick, or you're porting those 100,000 line legacy codes that maybe are already Fortran 77 or older, and you just want to get this to this new machine that your management procured for you. Or actually you're having a larger application, and there are some performance critical sections, but there's also a whole bunch of glue code in between, where you just have to do some data management or something, and then you've decided to use OpenACC for that. Then if you're programming, there are typically 5 results you're getting if you're programming. It's first you get compiler errors, which is what happens to me all the time. Then your program crashes, could also go out. Number 3, program produces wrong results. Number 4, program runs, results are correct, it's just painfully slow, and you have no idea why. And then number 5, program runs fast and correct. Unfortunate thing is that the likeliness is going this way. So to kind of help you getting to the point where you want to be, which is down there, performance tools can help. And at the moment, your performance engineering workflow, if you're trying to optimize things, typically is you kind of modify your code in some form, or you do certain preparation to kind of as a prerequisite for the optimization, meaning you throw in some printf statements, some timers or something, or you go to the command line and say gprof, or you've installed gprof as your preparation, or maybe you're doing some little things to insert some probes or something. Then you run your measurement. Basically, you're executing your application with a performance monitor attached. So you're collecting performance data there. And maybe if you're doing instant profiling, you're already aggregating it there. Then you do some analysis. This is basically you looking at the data, trying to make sense of it. And so you're looking at some metrics, utilization, you name it. Typically this is very application specific, because you know what's good behavior for your application and what's not. And it can be very different from application to application. It's not always flops. Sometimes it's updates per second or whatever. And then you've learned something from the performance data you acquired. You determined this is a bottleneck. I need to optimize this, and then you start tweaking this little aspect of the whole application. And at some point, then you kind of start over. You see what was the impact, and until you're satisfied. OpenACC at the moment doesn't have a standardized performance tool interface. So there are some vendor-specific things. So for example, the Cray environment, their Cray performance tools, they are OpenACC aware. The downside is that getting the Cray environment, software environment, comes at a price tag of at least $250,000, because that's the smallest Cray machine you can buy. They kind of tie it to their hardware. Other things like, for example, the PGI profiler just give you static profiles. They don't give you any flexibility. If you're not satisfied with what you're getting, then well, tough luck. Then you're basically back to my first slide, and you're reading tea leaves again. And the other thing is that most vendor tools don't have the scalability of the tools that is required to go along with the applications. So if you're doing full system runs on Titan, and you're trying to use CrayPad with this, good luck. Because basically, if you're doing tracing at that time, you've created an I/O problem, because you're spitting out so much data that it doesn't really help you. or that you have to be very careful of doing this. So you want a performance tool, and typically those are research-based. That can actually, cope with such an environment and with this demand of scalability for the performance tool itself. And with NVIDIA CUPD, that's the tools API for CUDA. This set a great example of how collaboration between a vendor, in this case for CUDA, and the research community can actually set a good example of how such an API could look like. How you can agree on certain demands, what kind of data you need. And the interesting thing is that CUPD is actually now the profiling interface that's even used by NVIDIA's own tools. So they've basically given up maintaining 2 APIs only for certain specific things, and they use the same API that us as researchers for our performance tools use. So you kind of, everybody's getting the same data. So the interesting thing is that no matter what you're doing, so seeing or looking at OpenACC in the broader context, if you're doing OpenACC on just one GPU, that's fine. But typically, especially if you are like in the HPC world, it's embedded in a larger context. You maybe have a hybrid MPI plus OpenACC application, or maybe you're even crazier and you're doing MPI plus OpenMP plus pthreads plus CUDA plus OpenACC. It's all possible. You can combine them all. And what I'm trying to say is that no matter what kind of parallelism you're doing, no matter how you do it, there's almost everywhere some kind of performance tool support. And there are performance tools out there that cover the whole range that you can use, so that they can actually monitor as you're running your MPI plus threading plus offloading application. They're actually recording everything that's going on and can present that to you, create you a profile of that. The interesting part is, now what can you do about OpenACC directive-based offloading? Doesn't have a profiling API yet, but wouldn't it be nice to have one? So at this point, it would be my moment to thank Michael Wolf right here from PGI for working with us on this, also in the OpenACC committee for prototyping something. So what you have at the moment is some profile-based stuff, the PGI profiler that if you turn a certain environment variable on, it will give you some things. You can use CRAPAT. If you want timelines, so actually like a full event log and then look at what happened at certain amounts of time, you can use CRAPAT. It doesn't scale to like more than 1024 processes because mainly of how they handle the data logging and the analysis. If you want to go to larger scales, there are research-based tools. The main one that I'm also involved in is called ScoreP. That's the performance monitor that scales to full systems like Titan. So we have done full system runs of applications of Titan where you're like spitting out terabytes per minute of performance data. But you can still analyze it. So we still have an infrastructure to handle that data interactively. And there is a technical report out on the OpenACC website that we've worked on together with the other OpenACC members to propose a tools API for OpenACC so that you have a standardized API that performance tools can use that, if you think that you know better to do performance analysis than us, which is fine, you probably do, then you can use that API to hook into the OpenACC runtime to see what the OpenACC runtime is doing, to determine what your application is actually doing in this kind of missing middle. So at the moment, we have CUPD underneath for the CUDA level. We can do all the other source code instrumentation on top, but what's happening in the OpenACC runtime is hidden at the moment. Having a standardized interface for this would enable kind of a wholesome performance analysis that actually shows you on every level what's going on. So there's this TR out there. You can go and read it, provide feedback. We're hoping, or I'm hoping, that this API will be part of the next version of the standard. And hint, hint, somebody needs to do some work on this. Basically how it works in a nutshell is the performance monitor registers callbacks with the OpenACC runtime so that as you're basically your application is this kind of what you're doing right here. And this is not your application. That's it. Basically the ScoreP tool, or your gprof, or whatever you're using, whatever your OpenACC capable performance tool is. It registers those callbacks, not for every routine, just the ones that you're interested in, depending on what you want. And for example, as you enter a data region, what's happening behind the scenes is that the compiler introduced a call to the OpenACC runtime that will then, because you've registered a callback, we get the callback that you entered a data region. And same on sync if you do an OpenACC wait or whatever. So everything that you've registered a callback for, you will be told that the host is now doing some OpenACC specific work. It's not spending time in your application, it's actually spending time in the OpenACC library. And with this, you can track this and you can create profiles, how much time was spent in the application, how much time was spent in CUDA activity, how much time was spent in the OpenACC library, for example. So what does it look like? Bringing in the visualization tool that we're developing in Dresden. It's called Vampire. Basically what you're having on the left side is timelines and then profiles on the right. What we're looking at is one of the spec benchmarks, SpecExcel OpenACC benchmarks. It's pure OpenACC, so no MPI included here just for simplicity. So we're seeing this all being green. Kind of the legend down here says that means application. I see a profile right here. The interesting thing, if you do tracing, is that you get profiles for arbitrary time intervals. So what you're seeing all the way up here is kind of a thumbnail of the overall performance data that you have, overall timestamps. And we're only looking at this very last portion right here. So only what's highlighted right here. And we see a profile, how the functions are distributed in this time interval. And we see, well, there's a function called calc3 that is spending most time, then calc2, the same. So, if you were to optimize this, you would go into calc3 now and see, how you can tweak this. The interesting part is that this is actually an OpenACC application, but without OpenACC support, the only thing you can do at the moment is basically tell ScoreP, I know that this will use CUDA in the backend because I only have NVIDIA GPUs in my system. So, okay, let's turn on CUDA profiling within ScoreP, and what now happens is it will also record all the CUDA activity that's going on. So you now see more colors appearing. Basically, that's just color coding things. You see CUDA API calls. They are in this cyan color. And then you have CUDA kernels. You see an additional thread appearing here. This is basically your CUDA device stream that is visible. You see mem copies going on. Those are the black lines right here. So those are the data transfers. And now the good thing is, or here in the blue, you see the profile of your CUDA kernels. And the thing is, you didn't write any CUDA at all. So what you're seeing here is what the OpenACC runtime and compiler have created for you. So you have no influence whatsoever over this, because those were generated for you. So although you might now get drilled down to a point where you see, if I were to optimize this kernel, this would really improve my runtime, you have no idea where this kernel came from, because it came from some OpenACC region. I mean, the good thing is that PGI is actually pretty good about naming this stuff. So they are not, coming up with random names. There's actually, a file name and a line number that's associated right here. So you can actually get to a point where this came from. But this is basically their decision. This is nowhere in the OpenACC standard. And you might get another runtime where this is all called ABCD, and you have no idea what it is. So we prototyped something together with PGI. They gave us access to their profiling or their hooks into their runtime. And what you can do now is we can actually hook into the OpenACC runtime library, similar to what the the OpenACC tools proposal is like. And what you can now do is you have your master thread right here that's going into a data construct. If I split this out and basically say, tell me for this what actually the call stack looks like, you see there's this Shalo routine that's being called right here. You're going into this data construct right here, and the data construct just does more OpenACC stuff down here. There's some user code that's being called right here. And I can actually profile also the OpenACC activity, seeing where I'm spending more time. And now the really cool thing starts. I can throw all of this together, saying, I can see now my application in green, I can see my OpenACC runtime in yellow, and I can see my CUDA in blue. And I can actually see from the kernel, through the kernel launch, through the OpenACC compute construct, to the OpenACC data construct, to my application, where things originated from. And now I get the full picture. Why a certain kernel is executed, how it's tied to a compute region, a compute directive that I have in my kernel or in my application, and what the performance impact of that is. Maybe I'm transferring too much data, and I can restate data clauses that I'm using, or you name it. You now have the full picture. You see everything, and now you can actually start tweaking your OpenACC and see the impacts that it has on your underlying CUDA code, or if you were doing OpenCL underneath, ScoreP also supports OpenCL. It doesn't really matter as long as you have some kind of tool support on all levels that you're using. You get a full picture, and you're actually able to do the right things. Let me just skip over this real quick. Kind of to sum it up, why should you care about this? If you cannot see what's going on, you're never able to know what's actually going on. And you cannot understand why it is the way it is, and you'll never be able to optimize your applications, and you'll be stuck reading tea leaves. Thank you.